Continuing on with chapter 26, we're now going to look at resistors in parallel. So in parallel just means this. It means I've got some battery, I come out here, and I have a resistor. There. So that's a complete circuit. But now I'm just going to tag another one onto this. And drawing it like this makes it kind of clear why we call it in parallel, but it doesn't need to be drawn like this. So for example, I could draw it like this. And as far as this circuit is concerned, that's exactly identical to whether I draw it here. I could have drawn this resistor down here, and it would have been the exact same drawing. So now let's just do R1, R2, R3. Okay, so what's the point here? Oh, okay. So the point here is we're going to do the exact same thing that we did before. I told you the rules to go by. What's the first thing we're going to do? We're going to look at this point and say this is at, if this is V, this is at V. This point here is at V. This point here is at V. Come back this way. This is at 0. This is at 0. This is at 0. So my potential difference across R1, R2, and R3 is V. All of them, each of them, have a potential difference of V across them. Okay, what's the next thing? Ohm's law. V equals IR. V equals IR. So I know V and R, so now I'm going to get these currents. So I know I1 is just, no, I don't think those other pens are working, so I'm going to just try this. I'm going to just do it here. V over R1, this is this current right here. V over R2 is this current right here. I'll just draw it like this. V over R2 is our current there. And I'm going to draw it over here. V over R3 is our current right here. Okay, something else that you need to know, you need to be really clear on, let me say that. What we just calculated was the current between right here and right here, or right here and right here, or right here and right here, right? We knew the voltage across here, we knew the resistance across there, therefore we knew the current. You need to be aware, however, that once again, the trivial way to think of Kirchhoff's law, or just think of a stream in the woods, if you calculate the current between this point and this point, there is nowhere else for it to go until you get to a junction. So if I calculate it between here and here, it is exactly the same amount all the way from here to there. Same thing here. It's exactly the same amount from here to here. There is nowhere else for that current to go. Same thing here. Here, it's the same all the way from here to here. There is nowhere else for that current to go. So, right here, what do I have? I have V over R3. Oh, I'm sorry. So now we're moving on to the next thing. What's the next thing? Kirchhoff's junction rule. The amount of current leaving a junction must equal the amount of current coming into that junction. And you can also do it the other way. The amount of current coming into a junction must equal the amount of current going out of that junction. The exact same thing. I'm just going to do it this way for now. So I have V over R3 that comes right down to here. But what do I have right here? I have V over R2. So what do I have right here? Junction rule. This is one stream. This is the other stream. The two streams come together. The amount of current leaving this point must equal the amount of current going into it, which is V over R2 plus V over R3. Then what happens right here? Now over here I have V over R2 plus V over R3. And what do I have coming in here? V over R1. So now here I have V over R1 plus V over R2 plus V over R3. I've got all three of those together, and that's the current that's right here. Now, all the way from here, all the way through here, all the way over to here, there is nowhere else for the current to go. Therefore, once I have figured out what the current is right here, I know what the current is all the way until I get to right here. Okay, so now you ask the question, oh, well, how do I decide now? How do I decide how much current is going here or how much current is going there? Or perhaps a better question, how does the current decide how much of it should go here and how much of it should go there? And the answer is, you already figured it out. You don't need to figure it out again. Because you knew the voltage was here, you know what current is there. And you know what current is here, and you know what current is there. Therefore, you know that here we have V1 over V over R1 plus V over R2 plus V over R3. But right here, V over R1 is going this way. So what's left to go this way? V over R2 plus V over R3. Then I get to this point here. I know V over R2 is going this way. Therefore, V over R3 is the only amount that's left to go in this direction. And we're done. Okay, so now we have the question. So what is our total current that's going through here? Well, we have V over R1 plus V over R2 plus V over R3 equals the total current. Well, once again, think about what we're trying to do. What we're trying to do is we're trying to say, okay, let's pretend we didn't know what was out here. What one resistor could we put over here that would act exactly the same as all of this? Well, what does that mean, act exactly the same? What it means is Ohm's law. V equals IR. What would that one resistor be to get the same amount of current? Well, what is that same amount of current? It would be V over V over R, and I'm going to go ahead and put EQ for, once again, equivalent, R equivalent. V over R equivalent would be equal to the total amount of current. Well, what's the total amount of current? This plus this plus this. So now I have an expression here. I'm going to divide all these by V. And what I want to get is this R equivalent. So I have 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over R equivalent. Well, I want to make this actually R equivalent. So what I'm going to do is I'm going to take this to the minus 1, which means I need to invert this as well. I'm going to invert that whole thing. The whole thing. This is a step that people often forget. So what this means is R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So, or 1 over R1 plus 1 over R2 plus 1 over R3, that whole quantity inverted is what the equivalent resistance is. So, what is this configuration? This configuration is for resistors in parallel. In parallel. And so, the equivalent resistance for resistors in parallel is calculated this way. All right. Your book does a very good job, I think, of talking about seeing whether or not this makes sense. And we actually talked about that in class a little bit when we used the water wheel analogy, and you guys all got that. So I think you'll understand why it is that there is a higher resistance when you put resistors in series, like those two water wheels where all the water that comes through needs to get both of those water wheels going, or, why that is a higher resistance, and if you go the opposite way, and if you put one water wheel and another water wheel, all next to one another, now you have more paths for the water to leave. And is it easier for water to flow? Would we expect more water to flow? Yes. So now what do we have? We have a lower resistance when we have all three of those in parallel. Your book has a discussion of that as well. I think it's pretty good. Okay, that's that for resistors in parallel.